Okay, let's go ahead and get started. So what are we going to be doing today? We're going to be able to take the antiderivative of a function. So basically, the idea is like what we did last week. The antiderivative is just doing the opposite of what you would have done to get the derivative in the first place. All right, and so our ability to go back and forth is important. You know, we can't really talk about adding unless we also talk about subtracting, multiplying and dividing, squaring and square rooting, exponentials and logs, and then derivatives and antiderivatives. And so it's important that we're able to do this. So a couple things I wanted to show you. These two are like really common, most important, I think. This top one is called, it's basically the reverse of the power rule. Right? So it's basically the opposite. So instead of making the exponent go down by 1 and multiplying by the old exponent, we're going to make the exponent go up by 1 and divide by the new exponent. And that's all we're doing. So if you're integrating x to the fifth, if you're taking the antiderivative of x to the fifth dx, then the exponent goes up by 1. You divide by that new number plus c. And we'll talk about this plus c a lot today because it's important for a lot of reasons, and we'll go over that a lot more because I know we talked a little bit about it before, but I want to talk about it more. And then this right here, this is a visual to try and help you with sines and cosines, because you know that the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine is sine again. So this just sort of helps you visualize it so you can cycle forwards and backwards. The blue direction, where everything's pointing, that's integrating, taking the antiderivative. The red direction, following those arrows, that's taking the derivative. All right? So let's look at this. I wanted to show you this. This is what's called a integral table. This right here has all of the basic derivatives along the left side and all the basic antiderivatives on the right side. And what you'll notice, hopefully, is that they correspond to each other, right? The derivative of a number is 0. The integral of 0 is a number. The derivative of x is 1. The integral of 1 is x plus potential constant. Power rule, right? Derivative of x to the n is n times x to the n minus 1. Same power rule I showed you earlier. The integral of x to the n is you're going to raise the exponent by 1 and divide by that new number. The derivative of e to the x is e to the x. The integral of e to the x is e to the x, right? The derivative of natural log is 1 over x. The integral of 1 over x is natural log. The derivative of a number to a power is a number to a power times the natural log of x. That should be an n. I don't know why. That's a typo. The integral is, you know, the opposite situation, right? Here it's times, here it's divide, right? The integral of cosine is sine, the derivative of sine is cosine, etc., 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 all the way down. Even the things that we talked about. If we know the derivative of tangent is secant squared, if we integrate secant squared, we get tangent again. And so on and so on. And here's even the Here's even some of the inverse trig stuff, right? Arcsine, arccosine, arctangent, arcotangent, arcsecant, arccosecant. They all it flips back and forth. All right, if we can do one way, we can do the other way. What I'll do is I've got this as a image file. I will share this in the Google Classroom so that we know. All right, so let's do these. So we're going to take the antiderivative, and we're going to say that c equals 0. So 11x to the 10th, I'm going to take the antiderivative. This is the symbol for the antiderivative. It's a big, long, stretched out s. We'll talk about why that is later. We'll get into the guts of this later, but right now, dx. And this is an important operator in there. Whenever you're taking the integral, you do have to have the differential here of the variable that you're working with. So if taking the integral of, if we're finding the antiderivative of 11 times x to the 10th, we're taking the integral of 11x to the 10th dx. And so once again, we're going to use that power rule, raise the exponent by 1, and then divide by the new exponent, right? Raise the exponent by 1, and then divide by the new exponent. And then once we cancel everything out, and also don't forget our plus c, we cancel everything out, we end up with 11. 11 divided by 11 is 1, so x to the 11th plus c. And then we want to know when c equals 0, so we're going to let c equals 0. And then we get just x to the 11th, right? So that's part A. Part B, same thing. X cubed, we want to integrate that with respect to x. We're telling ourselves with respect to x right here. So raise the exponent by 1 and divide by that new exponent. And voila, 1/4 x to the 4. And then the other thing I want to remind you is that it's okay to break this up. As long as it's a plus or minus sign, you're allowed to break these up. So let me erase all this so I make some room. Let me erase all this so I can make some room. And we're going to integrate this whole expression with respect to x. And if I do that, then I can just do each of these separately. What I'm really doing is I'm just distributing this over everything. So first things first, raise the exponent by 1, divide by the new exponent. Minus, raise everything, divide by the new exponent. And then again, you don't have an x here, so we're going to integrate. This is going to become 18x. And then what we can't forget about is the plus c, right? Can't forget about that plus c. But then we know that c equals 0. That's what they're telling us. Hey, make c equals 0 for this one. And so we can just ignore that and have our final answer be x cubed over 3 minus 3x squared over 2 minus 18x as our final answer. Because for these, they're telling us c equals 0 already. We don't have to do any more work to figure out what c is. Okay? And then if you wanted to, you could take the derivative of each of our answers and you can show that, hey, this gives me back what I started with, so I have to be right. Okay, let's do the next one. So now with these, remember, the thing that gave us 1 over x when we took the derivative was natural log. So if I integrate it, I better get it back up there. So let's take the integral of 1 over x with respect to x. Well, the thing that gives us this derivative is natural log. So when I integrate, I get natural log of x plus c. And again, they're telling us, hey, c equals 0. So my final answer here is just natural log of x. Now here I want to show you with b, here's an easy way to make this not annoying. Because what does this 5 have to do with anything? Nothing. Take it. Factor it out of the integral. And then it's the same problem again, right? And once again, the plus c equals 0, so and then again, if you've got different things, you can do them separately. Take the integral. Right? Take the integral separately. Do yourself the favor of factoring out all the things that you don't need. And then, like, okay, so the integral of 1 here, you get x. You can pull out that 2, right? And so what the integral of 1 over x is still natural log of x. Now there's just 2 times natural log of x. And then do that plus c, and then they're telling us, hey, c equals 0. So our final answer, x plus 2 natural log of x. And one thing that our book does that I like is they have us put absolute value signs around the x here. And I'm going to explain why right now. So the thing that we know about the natural log is that the input for the natural log has to be bigger than 0. So, but x doesn't have to be. So in order to have the same domain and the right stuff going on inside there, and for it to not cause problems, we always, when we're working with natural logs, we assume that x is positive. So here, rather than saying at the very beginning, hey, let x be bigger than 0, we just in our natural log, when we go from here to here, we put the absolute value sign in. We didn't have to do it the other way because we were starting with a natural log. And so the negative numbers were all out of commission anyway. But here we're starting with 1 over x and we're turning it into a natural log. So we have to actively say no negative numbers on the inside of the natural log. So my recommendation to you is just whenever you're doing an integral and a natural log pops up, put some absolute value signs there. Just treat that as your new natural log grouping symbol, okay? That's sort of the way that my AP Calc teacher 15 billion years ago told me to do it. And it helps, and it means that you won't get anything wrong, which is good. Yeah? All right. Let's move forward. So remember, we were talking about sine and cosine. Remember, when you take the derivative and there's like something else inside, you have to do chain rule. And but you know, you did, and it basically, hey, take whatever's on the x and multiply it to the outside. It's going to be the same idea here. When you integrate, take whatever's on the inside of the sign and divide, right? So when we integrate this, well, let's put the negative 10 out here. We're going to integrate sine of 10x with respect to x. Okay, well, if I go back and look, I'm integrating sine, so I'm following the blue, because that's a negative cosine, right? So I'm going to integrate. So we got the negative 10 out here times negative cosine of 10x, and I divide by the coefficient, plus c. So let's clean all this up. The 10 and the 10 cancel out, the two negative signs cancel out, so we are just left with cosine of 10x plus c. And then we look, okay, they did say that c equals 0 for this one again, so we just end up with cosine of 10x as our final answer. Ta-da! Going to be the same thing with the rest of these, right? Same idea and the same spiel that I'm giving. Hey, look at what you've got. Make it easier for yourself by simplifying everything so that you don't have to work as hard. If you want to take the antiderivative of 9 sine x, you can just pull that 9 out. Well, the integral of sine is negative cosine. So our final answer, once we remember that we're saying that c equals 0, is just negative 9 times the cosine of x. And then the same idea goes here. If you have two different things that are connected with addition or subtraction, just integrate them separately so that you don't have to think real hard. Don't try and do it all at once, right? Don't try and do it all at once. If you do it all at once in your brain, it's going to be a mess. Just take the integral of the sine of 10x. So you're going to get minus 1/10 cosine x minus the integral of this thing. Well, two minuses make a plus. Divide by the 9, so it'll be cosine of, well, this is a 10x. 9x here, right? And you could even, if you wanted to make it look pretty, cosine of 9x minus cosine of 10x over 10, right? Just to make it look prettier. And that's the whole thing. So here we've got, I'm trying to integrate cosecant squared. Well, which one is that? I think it's cotangent, I think. Let me double check. And I don't remember all this. Yeah, the derivative of cotangent is negative cosecant squared. If I integrate it, if I integrate cosecant squared, if I maybe write letters, CSC, there we go, squared x with respect to x. If I integrate this, well, if the derivative of tangent is negative cosecant, the integral of cosecant squared had better be negative. All right, that's what I said. Cosecant and cotangent. Yeah. So the derivative of cotangent is negative cosecant squared. So the integral of cosecant squared had better be negative cotangent squared, or negative cotangent, right? That's it. And then again, plus c, but hey, c equals 0, so I'm done here, right? With this one, once again, don't overthink this. Put the 8 over 9 outside, and then just do this. Well, I integrate, that means I'm dividing by this 1/9, which means I'm multiplying by 9. I'm gonna get it. I'm gonna get there someday. There we go. X over 9 plus C. And then just clean it up. There's a 9 on top. There's a 9 on bottom here by chance. There's a minus sign here. Bring that minus sign down here. And that plus C, remember C equals 0. So, and notice I'm writing this, hey, at C equals 0, just so I remember. But that's your final answer. And then, same thing here. What are you going to get? You're going to get the negative is going to become a positive here when we integrate, right? Because it changes signs. And then we're going to divide by this 9 over 8. So for part C, we're going to end up with what? 8 over 9 cotangent 9x over 8. And again, you can take the derivative to double check that your answer is right. And that's fine. It even tells you, hey, check your answers by differentiation. They're not going to make you check your answers by differentiation, but you could. If it helps you to make it easier to know that you are correct, do it. Here's with the exponentials, right? Well, we know that when we do e to the x, we get e to the x. And when we're taking the derivative, if it's e to the something x, we multiply by the something, right? So if we're integrating, we're going to divide. So this was e to the 9x. With respect to x, we're going to integrate that. And we get 1/9, because we divided this time, e to the 9x. And again, c equals 0. I'm not going to bother putting the plus c. Same thing here, right? For part B, what we should end up with is this same thing divided by -4. So for part B, -1/4 e to the -4x. For part C, dividing by 1/5 is the same thing as multiplying by 5. So we end up with 5 e to the x over 5. And again, these will all have plus c's, and here for each function when c equals 0. So we're going to get rid of them anyway. All right, that's all we're doing with this stuff. It's all just doing the opposite of what we did earlier. Like here, remember when we did this, took the derivative times the natural log of 7, right? But here we're integrating, so it's divided by the natural log of 7, right? So here, this one for part A, you better get, when you take the integral, you write it out, you're dividing by the natural log of 7, right? So 7 to the x over ln 7. Here with this one, there's a number of ways to do it. I think you take a second, and so a negative x means take the inverse of what's here, right? Make this 1 over 5 to the x. And then you can be like, well, okay, integrate 1/5 x, 1/5 to the x over the natural log of 1/5. Same thing here. 6 over 5 to the x power. Well, you integrate that, and shouldn't you just get 6 over 5 to the x divided by the natural log of 6 over 5? Again, don't make this complicated. Don't make this complicated. It's not difficult if you just remember the other direction and just do it in reverse, right? Whatever you did before, do it again, but backwards. These our power rule ones, they're just ugly looking, right? Look at what I'm going to do. I'm going to say, well, I'm going to raise the exponent by 1 plus 1, and then I'm going to divide by that. Now, I don't know if they're going to make you rationalize the denominator here. But, you do the rationalization, multiplying by the conjugate, radical 7 minus 1, and you'll get something like this. That's if you were to rationalize it, but I'll be very honest with you. If you were putting down anything other than that, you're wasting time. Leave it like this. There's no reason not to. Remember, I keep saying on the AP exam, if you're taking time to simplify your answers, you're wasting time and you're letting your grader off easy. Make it so that they have to work for their money. They're getting paid and they're getting a free hotel room and free food and free airfare to that place. Make them earn it. Same thing here. Okay, look. X to the 2 pi. Yeah, but we're going to integrate that. Make the exponent go up by 1 and then divide by that new number. Same thing here. Make the exponent go up by 1. Well, minus 1 plus 1 cancel out, and then divide by. And again, I'm not going to make you rationalize, but this is what it would be rationalized, I guess, if you want to see that. But like, again, if you're not giving me this answer, you're wasting your time. Make them earn their pay. All right. What else do we have? Yeah, so these are all just inverse trig. Do I have all of them? I know those last two are tangents. Arc sine, I think, is the other one because it's positive, right? Yeah. Okay, so this is going to be arc sine. And again, this 9, bring it out. Because you want to just have the base form in here. So this is 9 arc sine of x, right? Plus c, but c is 0. This one, these are both tangents. Let's start with this one because this one is easier. Because it's in the right form. You just pull out that 4 and then do your integral of 1 times 1 plus x squared. So this is just tangent 1/4 arc tangent of x. And again, plus c, but c is 0. We don't need to do the plus c for this one. And don't forget your dx's, I guess. With respect to x. And then here, okay, so with this one, here's where this one is annoying. It's because it's sort of out of format. It should be 1 and then 1 plus u squared. Well, what is u squared? We need to rewrite this so that it's something squared. So this 100 times x squared, we can rewrite that as 10x, the quantity squared. So again, chain rule thing we have to deal with. Normally we would be multiplying by 10, but since we're integrating, we're dividing by 10, right? So the integral of 1 this ends up with 1/10 tangent of 10x. Tangent inverse arc tangent. There we go. And we'll talk more about, so we talked a little bit about this. Here's the sort of the format that we're dealing with. Eventually, we're going to talk about the inverse of the chain rule, which is referred to as U substitution. I think we'll talk about it when we come back. And the thing about U substitution is that once you see it, you'll never unsee it, and it's great, but it's that building that pattern. And so by doing this and getting used to seeing what the patterns are supposed to be, we're going to build that up together. So now, here the directions just say find the indefinite integral, which means that our answer should contain plus c, right? So we're going to integrate. And remember, I said we can integrate each of these separately. So let's do this. We integrate 20x. This is 20x squared over 2. We integrate the 7, and that becomes 7x. And then we have to remember to put down our plus c. And then we can clean it up, make it all pretty. There's our final answer. This is the family of functions that result, that give you this as a derivative. If I take the derivative of all of these, I will get 20x plus 7, no matter what c is. Here's another one. I put this one on here on purpose because it looks ugly. It looks weird. What is happening here? Why would we do this? How do I take care of this? I don't know what function makes that happen. No, but we can make it look better, right? Distribute this x to the negative 4, right? Make this the integral of x to the negative 3 plus x to the negative 4. Then you can split it up, do each piece separately so that we're not overthinking. And we know how to do this. Raise the exponent by 1, divide by the new exponent. So we've got x to the negative 2 over negative 2, minus, right? And then here we're going to have a minus. I'll put the minus sign down already because I know that this is going to be negative. Raise it up to the negative 3. And I've divided by negative 3, but I brought the negative sign up here. Plus c. And again, unless they give you specific directions not to include the plus c, like the ones we had earlier where they say, hey, c equals 0 already, okay? Here, if you do not include the plus c, it will not be correct. It won't, because it's not right. Indefinite integrals create families of functions because it doesn't matter what you're adding when you take the derivative of just a number. It goes away. It doesn't matter if the number was 12. It doesn't matter if the number was negative pi, 52, negative 6.8, whatever. That going away. And we're just going to be left with all the x terms that were around. So just be aware. This does have meaning, and it does make a difference. All right? Let's do another one. We've only got a couple more. So here, and this is why the plus c is so important, because here, and I'm going to use a term, a differential equation. That is what this is. The derivative equals this function. That is what we would call a differential equation. So what am I going to do? I'm going to take this dy over dx equals 10x minus 3, and I'm going to take the integral. Well, how am I going to do that? There's supposed to be a dx over here. That's okay. I can take this dx and move it up. So what I'm going to have is dy equal 1 dy. Let's say it like that. 1 dy equals 10x minus 3 times dx. Well, now I can integrate both sides. Let me do that. Well, what's the integral of 1 with respect to y? So it's y, right? Let's integrate this. Well, what's the integral of 10x? What's the integral of 3? Don't forget your plus c. And now we're going to use this initial condition when x equals 7, y equals 0 to find our specific value of c in our specific function that we're actually talking about, right? So let's do that. Well, x is 7 and y is 0. So 0 equals 7 squared is 49 times 5 times 10 divided by 2. Okay. Minus 3 times 7 plus c. Now let's solve for c. 245 minus 21 is 224. And so when I subtract the 224 over, c equals negative 224. And so my final answer, and I'm going to write it the way that I'm sure they would want to see it, y of x equals 5x squared minus 3x minus 224. And you can check. If I plugged in 7, then I should get 0 as my output. Yeah, right? This is 245 minus 21 minus 224. Better be 0, right? That's how we got that in the first place, right? All right, let's do a couple more. So here, they're actually going to make you do this a couple times, right? Here, they're giving you the fourth derivative, and we're going to have to go through and do the initial condition with a third derivative, a second derivative, a first derivative, and then a whole thing. So if this is y to the fourth, let's find y to the third. The third derivative. Well, let's integrate. We integrate negative 3 sine t, we get 3 cosine t. We integrate 4 cosine t, we get 4 sine t plus c. And they tell us that when t is 0, y is 9, right? So let's figure that out together. T is 0, cosine of 0 is 1. Sine of 0 is 0. So this is 9 equals 3 plus c, right? Well, so then that c here equals 6. So let's regroup. Y triple prime equals 3 cosine t plus 4 sine t plus 6. There's my y triple prime. So now let's do that again, and then we'll have y double prime, right? I'm going to go ahead and erase this. Hope that's okay. So I've got y triple prime now, and I'm going to integrate that. Well, the integral of cosine is sine, so y double prime, 3 sine of t. The integral of sine is negative cosine, so this will be minus 4 cosine t plus integral of 6 is 6t, right? Now I know that y double prime of 0 is negative 4, so x is 0, y is negative 4. So again, sine of 0 is 0, cosine of 0 is 1. So we've got negative 4 equals negative 4 plus 6 times 0 plus c. I keep forgetting the plus c. So look, negative 4 and negative 4 cancel out. This is already 0. Here, c equals 0. So my y double prime is just this without the plus c, right? So let me make some more room. Get rid of that because C equals 0. So this is my y double prime. Now let's find my y prime. Let's integrate sine and we get negative cosine. Let's integrate cosine, we get sine. So this is, let's integrate 6t. That gives us 6t squared over 2 plus c. Let's use our initial condition. Y prime of 0 equals negative 3. So negative 3 equals negative 3. This is 0. That's going to be 0. So again, C equals 0. Hey, looking good. Last one. The C is 0. I can just leave this here. I don't have to do any kind of rewriting and stuff. And let's find y. Integral of y prime is y. Integral of this. Integral of cosine is negative sine. So we got 3. Oop. Integral of cosine is sine. There we go. Again, think about what you're doing. Pay attention. Have your references nearby so that you don't forget. And if you do, catch yourself. Double check all your work as you think about it. Integral of sine is negative cosine. There we go. And then this was 6 over 2. This is 3, right? Let's make this easier on ourselves. Integrate. That's going to cancel out, and then we're left with plus c. And so, at 0, this is 0. This is 1. This is 0. So we're left with 3 equals 4 plus c, right? 4 times 1 is 4. So c here is negative 1. And so our finalist answer here, what does y equal? Negative 3 sine of t plus 4 cosine of t plus t cubed, right? You can cancel that out here, so you don't need the 3 over 3, plus, what is c here? Negative 1. And that's our whole thing. All that work. But it's the same concept. It's just doing the exact same thing again and again and again and again and again and again and again. All right? This last one. So what they've done here is they've given a visual. They've given a visual. Well, I need to, here's the differential equation, and here's all the, this is a summary of all the ones. There's actually ones in between all of these, because this is just when, like, here's C is 0. Here's where C is a half, 1, 1.5, 2, etc. All that good stuff. So what we need to do is we need to take the integral, same way we just did. So what we end up with here, y, well, what's the integral of 1? That's x minus 1/3 plus 1, that's 4/3. We got 4/3 x to the 4/3 divided by 4/3, right? So these actually 4/3 and 4/3 cancel out. Hey, nice. Plus c. So let's rewrite this out all nice and pretty like, so it's easy to figure out. And I need to find the equation of the curve that passes through the labeled point. 1, 0.5. Well, x is 1, y is 0.5. So here, 0.5 equals x is 1 minus x is 1 plus c. Well, here, 4/3 power of 1 is just 1. So this is just 0, right? So c is 0.5. So now we can do our equation now. finally, this plus c is just 0.5. So our final answer here, x minus x to the 4/3 plus 0.5. Or plus 1/2. I don't know what the problem may be. It'll say, hey, only write this as a fraction, whatever. Then plus 1/2. But yeah, that's all we're doing. That's all this is. If you can do this, you can do anything.